Hey everybody, Dr. A here, and in this video we are going to be discussing the Poisson effect and Poisson's ratio. So the Poisson effect and Poisson's ratio is named after the French mathematician and engineer Simon Poisson. And basically what the Poisson effect tells us in mechanics of materials and material science is that whenever you have a load applied to a body, there will be a deformation in the direction of loading, and simultaneously there will be another deformation in the direction normal to the loading. And when we say normal in engineering, we mean perpendicular. So maybe pause the video and write this down in a notebook to lock it in. So let's look at an illustration of this. All right. So let's consider a rod, an axially loaded rod. Consider an axially loaded rod. Okay. So let's say we have this rod. And let's say it is being loaded axially. Remember, axially loaded means the load is applied along the longitudinal axis of the rod. And let's say that this is going to be a compressive force. Let's just call it C. And then let's say that the rod has an original length L naught and an original diameter D naught. Okay, so when this load is applied, this rod will tend to deform. Okay, so you think about it yourself. How is this rod going to deform when it is subject to this axial compressive load here? Well, as you could imagine, the rod is going to shorten in length somehow. Okay, so it's going to decrease in length. So I'm going to draw a deformed version of this rod right here. It's going to decrease in length. So this new length here, let's call it L, is going to be shorter than the original length L naught. So that is the deformation. That's because of the deformation in the direction of loading. Now, based on what the Poisson effect is telling us, is that in the normal direction to loading, which means for this example, it's the horizontal direction, or we could call it the lateral direction of the rod, we are going to have another deformation. Okay. Now, that deformation is going to take the form of what? Well, in this case, it's going to create an expansion in the cross-section of the rod, which means that this rod is going to tend to bulge out, okay? And when it bulges out, it's going to have a new diameter of D, where D is going to be larger than the original diameter D naught. So this is what we mean by the Poisson effect. You're going to have a deformation in the direction of loading, in this case, axial compression or a shortening of the length, and then simultaneously you're going to have a lateral expansion or a bulging of the cross section, thus giving a diameter larger than the original diameter. So let's draw some dimension lines on here. This, if we call this dimension line delta longitudinal, or since I showed it on both ends, we can call this delta longitudinal over 2. And this right here is also going to be delta longitudinal over 2. Then we can write delta long is going to be 2 times delta long over 2, of course, because I'm showing the deformation on both ends of the rod. And then similarly, if we draw maybe a center line here, and then we kind of superimpose the original diameter here, we can draw, I know this drawing's getting a little messy, but we're going to have this expansion of the diameter on either side of this superimposed original diameter that was here. And so we can call these two dimensions right here delta lat over 2. okay? So delta lat over 2 is happening on either side. So we can say delta lateral equals 2 times delta lat over 2. Because, again, I'm just showing it on both sides of the original diameter, so bulging on either side all around, okay? So that's for compressive loading. And then similarly, I'm going to go a little faster now, but similarly, we can have a rod subject to tensile loading, so T, tensile force T, and again, it has an original length and an original diameter. And then, of course, what's going to happen here, you're going to have an elongation of that rod, and simultaneously, you're going to have a decrease in cross-section area. So this new length here is going to be longer than the original length, and then, of course, the new diameter here is going to be smaller than the original diameter here. And then, of course, we could sketch some dimension lines similarly on this diagram. I'm not going to do that for this diagram, but it would have the same form. You have an elongation. You can call it delta long over 2 on either side of the lengths of this specimen, and then you can have a delta lat over 2 that shows the deformation, a compressive or contracting deformation in the radial or lateral direction. Okay, so so how does this all kind of come together? So this is discussion of the Poisson effect. What is Poisson ratio? Well, Poisson ratio is defined as the following. We use the Greek letter nu to represent Poisson's ratio. Okay, and I'll write that in parentheses here. This is the Greek letter nu. It looks kind of like the letter V, but it has a little serif on it. And Poisson's ratio is defined as negative epsilon lat over epsilon longitudinal or axial. Okay, so we'll say epsilon long. And, you know, sometimes we can say epsilon long is sometimes called epsilon axial because it's in the axial direction. So if you see epsilon long for longitudinal or epsilon axial, it means the same thing, okay? Now these epsilon values, these are strains, of course, right? So epsilon lat is called lateral strain, and then epsilon long, also sometimes called epsilon axial, is axial strain, okay, or longitudinal strain. Okay, so how do we calculate strain? Well, hopefully you remember that the basic definition of strain is just a deformation divided by an original dimension. An original dimension, okay? So for epsilon long, that would be a longitudinal deformation divided by the original length, and epsilon lateral would be delta lateral. Okay, and looking back at our original diagram, we can say it's delta lateral. Okay, now in our original diagram that I drew here, I showed it as delta lateral over 2 on either side, and I showed it as delta longitudinal over 2 on either side. So if you're looking at delta lateral over 2, but on either side it becomes 2 times delta lat over 2, then you would express this as delta lat over the original diameter, okay? Or, you know, you could say this is delta lat over 2 divided by the diameter over 2. So you could express epsilon lat, if you wanted to, as delta lat over 2 divided by the original radius. So just be careful with how you're measuring these deformations. Again, I prefer to show deformation on either side of the body that is being loaded and deformed. Okay, so but in general, this is what we call Poisson's ratio. All right, so for most like 99%, pretty much for most materials, let's see if I can spell that right. For most materials, we have a Poisson ratio that's between 0 and 0.5. For most solid materials, we have Poisson ratios that are between 0.2 and 0.4 for most solid materials. So that concludes our brief overview of what Poisson ratio is and how we can determine it for a loaded specimen. Thanks for watching. Please hit like and subscribe.